Okay, so welcome back, and now we're going to start talking about a couple of other tests that we can use. Now, using the limit of partial sums is a good way to see whether a series converges or diverges, but it is not always easy or even possible to come up with a formula that represents the nth or the kth partial sum. And so in those cases, we need to have other tests, and fortunately there are many other tests that we could use to test the convergence and divergence of a series. So two of those tests we're going to talk about starting today and going over subsequent videos is the test for divergence, the divergence test, and the integral test. So if we look at this series here, this general series, we know that for this to converge, a sub n must approach 0 as n approaches infinity. And so how do we know that? Well, if we look at the infinite series, a sub n, right? So we can represent the nth term. So if the nth term approaches 0 as n approaches infinity, that must be true in order for this series to converge. Okay? That means that this series here we can write as the sum, right? The infinite sum of what? Well, how do we represent a sub n? Well, we can represent a sub n by taking s of n minus the partial sum right before it. So if we take s of n and minus s sub n minus 1, that will give us the last term, the nth term, right? Now, if these two sequences, if the sequence of partial sums is convergent, right? So if we assume that those are convergent, then we can use the limit right? We can use the limit of this. Oh, so hold on. Nope, I don't want to do series, sorry. I want limit. There we go. Okay, nope. These should be k's because we're looking at partial sums. That's wrong. So, okay, now, so if we look at the sequences, right, so if we look at the nth term, and we say the limit as k approaches infinity of a sub k, which again we can write this as the limit of the difference between s sub k minus s sub k minus 1. So we could take the difference between these two partial sums, and that will give us the last term. Right? And so again, if you don't see that, just think of s sub k is equal to what? It's going to be equal to a0, or excuse me, a1 plus a2 plus a3 plus all the way up to a sub k, right? And then s sub k minus 1 is going to be a1 plus a2 plus a3 plus all the way up to plus a sub k minus 1. Well, we could extend this out and just add a term here, so right. So s sub k goes all the way up to a sub k. S sub k minus 1 goes all the way up through a sub k minus 1. And so, of course, if we subtract these two like we are up here, then all of these terms go away and we're left with a sub k. Okay? So now, if we look at this here, and if these sequences converge, right? What's going on with the limit of this? Well, the limit of this is equal to the limit of this. And so if we look at the sequence of partial sums, what's going on with this difference? Well, we can use the properties of limits and say, well, the limit of this is the same as, the limit of the difference is the same as the difference in the limits. So we could say k, the limit is k approaches infinity of s sub k minus the limit as k approaches infinity of s sub k minus 1. Now, what do we know about sequences? Well, if they converge, then it doesn't matter where they start. The partial sum is still going, the limit of the partial sum will always go to the same value. So in this case here, this is going to go to the same sum, right? Let's say this is going to go to the limit, which is, let's say, s, right? And so then, of course, this limit will also approach the same limit because, again, it's the same sequence, just different, positions or starting points, if you will. So then we get s minus s, which is 0. So if we're dealing with convergent partial sums, which means that the series is convergent, then we can see that the nth term must approach 0. Now, okay, so now what does that give us? Well, what that says is if, okay, so here's the if, right, if the series converges, okay, so if then what? Then a sub n approaches, so the limit of the nth term approaches 0 as n approaches infinity. So there's your if-then statement, right? So it's a conditional, so it goes one direction. So now this doesn't really help us, right? So if we know that the series converges, then this is automatic, right? So if this is true, then this must be true. But what if we don't know whether the series is convergent or not, whether it converges to a number or not, or whether it diverges? Well, how is this going to help us? Well, we can use the contrapositive of this, and this is where the divergence test comes in. Because the contrapositive of a conditional says, if not this, then not this. So that's where the divergence test comes in, because now what we're going to do is we're going to test for divergence. Okay? So the divergence is the contrapositive of this. What does it mean? It means that if a sub n does not approach 0 as n approaches infinity, then what can we conclude? Then the series must diverge. Then the series of a sub n of the nth term as n goes from 1 to infinity does not converge, or in other words, diverges. And that is the test for divergence. Okay? Now, it doesn't say anything about converging or convergence, but it does give us a way to test whether it's a series is divergent. Okay, now if it fails, okay, then be careful, because if this is not true, right, let's say it does go to 0. Let's say we show that, oh, wait a minute, a sub n does go to 0 as n goes to infinity. Well, that doesn't prove that it converges, okay, so that's too strong, right? So this is a necessary condition, right? It must, right? So it must, if this is convergent, then this must be true, right? But it's not it's a necessary condition, but it's not a sufficient condition, okay? So if we do show that the nth term goes to 0 as n goes to infinity, that's not strong enough to get us to convergence. So that's the limitation. Okay, so the best we can do is, if this is not true, if a sub n does not go to 0 as n goes to infinity, then we can say that the series is divergent, but we can't say anything about convergence otherwise. Okay? Okay, so now let's stop there, and next time we'll introduce the theorem.